This lesson has been developed in the framework of SCILED project. Module 3, Footwear Design Engineering. Unit 3, Engineering Footwear for Mechanical and Hydrothermal Comfort.
Lesson 3.4. Managing Bending and Torsional Characteristics of the Sole Structure. This lesson is structured as following.
Introduction. Simulating bending and torsion of sole structures by FEA. Optimizing the bending and torsional characteristics for sole structures.
Introduction.
Besides managing plantar pressures, it is important that bending and torsional characteristics of the sole structure are managed as well. These take place during walking, running and other movements. In ordinary gait, walking, there are several documented reasons why bending and torsion characteristics need to be managed. First, it has been proven that the bending characteristics of the sole affect the magnitude of the push-off forces, Sakajlo et al., 2007. Engineering theory as well as simulations with finite elements, Papayannis et al., 2017, have shown that there is high positive correlation between bending and torsion strain energy characteristics. Therefore, if a shoe is very bendable, it is also very twistable. Overall, in the usual urban environment when walking, the less rigid is a shoe, the better. The work required for bending and torsional deformation can be determined through physical testing or through simulation. Currently there are two approaches to simulating bending and torsion of sole structures, one based on differential rheological modeling, Azariades et al., 2007, Alemani et al., 2013, and one on finite element analysis, Papayannis et al., 2015. The former calculates forces moments, but the latter calculates strain energy. It is far more flexible with regard to the designs of sole structures that can be assessed, and it is far more practical with modern engineering software. Strain energy, the energy stored in a deformed structure, can be divided by volume of the structure, thus producing a strain energy density figure, which is scalar, i.e. not a vector, as it is the case with forces and moments, and structure independent, due to division by volume. It is therefore a very useful aid to assessing the bending and torsion characteristics of sole structures. It is also possible to further divide the strain energy density with the length of the structure, that gives metrics per unit length as well.
Simulating bending and torsion of sole structures by FEA.
Sole bending and torsion investigations can be carried out through multivariate differential modeling or finite element analysis, with the latter being the preferred option today, Azariades et al., 2007, Papayannis et al., 2015. Finite element analysis allows for the simulation of bending and torsional deformations of modern multilayer sole structures, applying realistic boundary conditions. Even then, the issue is how to interpret any strain energy density results. Papayannis et al., 2017, established comfort levels relating objective mechanical measurements to subjective perceptions, thus providing practical comfort evaluation at design stage. These have been derived as follows. First, bending and torsion simulations for key materials in relation to sole thickness were carried out and the results are presented in the figure on the left side. Higher Young's modulus and thickness lead to higher structural rigidity, as expected. Besides this material and thickness-based approach, typical multilayer and multi-material sole arrangements, benchmarks, of the market have been simulated and the respective strain energy density values are given in the table on the right side. All results correlate with expectations and working guidelines of the footwear industry. The analysis presented in the previous slide of the above graphs and benchmark characteristics along with industry perceptions led to the determination of strain energy density categories that correspond to subjective perceptive performance groups, Papayannis et al., 2017. These are given in the two tables from the slide. These tables allow for the determination of the comfort category of a footwear structure. They can also be used for optimization purposes. The most common optimization problem is the definition of optimum material arrangements for given layer thickness values and targeted comfort levels. This is because geometry is, mainly, defined in early design stages and then becomes subject to costly restrictions, for example last type, assembly technologies, thus, discouraging changes at later stages. There are several options when selecting algorithms for optimization. There are continuous or discrete tools based on screening, Lagrangian and multi-objective genetic options. Given the current state of technology and limited inventories, it is possible to produce adequate results within short time frames, ranging from 30 minutes to 48 hours, with simple screening discrete algorithms. Comfort levels are strain energy density intervals. Values closer to the midpoints of the intervals are more desirable when a specific comfort level is targeted, whereas values near the endpoints are deviating significantly from desired performance. Strain energy density sensitivity to thickness is higher for bending than for torsion. The clear demarcation of strain energy levels for bending makes optimization for a targeted strain energy density value and given layer thickness less susceptible to error than for torsion. Also, increases in bending rigidity positively correlate to increases in torsion rigidity. For reduced processing of overall bending and torsion behavior, bending optimization may suffice. A ranking discrete algorithm for bending and torsional optimization is described by Papayannis et al. 2017. It returns results between 32 and 34 minutes for problems involving 15 by 16 by 8 permutations of materials in a 3-layered sole structure.
Optimizing the bending and torsional characteristics for sole structures.
A study of the bending of the sole using various footwear materials to find their bending behavior was done by Papayannis et al. 2015. The sole dimensions are 290 mm x 120 mm and consists of an outer sole and a midsole layer. In order to simulate a typical polyurethane (PU) sole system of the market, the thickness of the outer sole was set equal to 5 mm and the thickness of the midsole equal to 10 mm. 4 of the most usual footwear sole elastomer materials were selected for the analyses and linear mechanical properties were assumed for each trial. The structure is fixed on its lower front side and the back part of the structure is bent upwards by a max angle 55 degrees. Calculated values for both maximum principal stress and strain energy are higher for increased Young's modulus of the sole material, indicating a realistic approach to assessing bending deformation characteristics of footwear components. This presentation of distribution for either stresses or energy quantities allows for problematic areas within the structure to be identified and sole design to be improved. According to the results of the analyses presented in the data from the Table 3, it is concluded that the soles are very flexible. According to Papayannis et al. 2015, torsion analysis can be conducted either by fixing the lower front part of the sole and rotating the heel part, or by fixing the heel part of the sole and rotating the front lower part. In the following example, the heel is fixed and an anti-clockwise rotational deformation has been applied to the structure of the sole. The table presents the results of the Fay analysis for the 4 material combinations selected. High values for principal stresses are due to boundary conditions that force Cartesian translation of points rather than rotational movement, Figure 9. Calculated values for both maximum principal stress and strain energy are higher for increased Young's modulus of the sole material, indicating a realistic approach to assessing torsion deformation characteristics of footwear components. According to the results of the analysis presented in the table, it is concluded that the soles are very flexible.